See, now we're discussing the topic is the escape velocity. Escape velocity. See, escape velocity means the minimum velocity. The minimum velocity required for an object escaping from a gravitational influence. See, escaping from a gravitational influence is called escape velocity. Now we can derive this formula of a escape velocity. Let us consider this is an earth. Now this earth of the mass we are considering the capital M. Its center is O and radius capital R. Radius is the capital R. Now the one object, so this is the object, the placed on a surface of a earth. Surface on a earth. Now this object is moving vertically upwards. Is moving vertically upwards with velocity v is equal to ve. V is equal to ve. The v is nothing but escape velocity. Escape velocity. And this object of the mass we consider the small m. And now when it's moving vertically upward direction, its potential energy is decreasing. Potential energy is decreasing and convert into the kinetic energy. See, that means the total energy can be remains constant. That means the potential energy plus kinetic energy is equal to 0 because of the total. We all know the law of conservation of energy. See, what is statement of law of conservation of energy? Energy neither create nor destroyed, but energy can be transferred one form to another form, and the total energy can be remains constant. The total energy is nothing but 2 is equal to 0. And now this kinetic energy is taken this side. The potential energy is equal to minus kinetic energy. See here the potential energy is nothing but gravitational potential energy. What is the formula for the gravitational potential energy? Minus G m1 m2 by R is equal to, we know that kinetic energy of the formula of mv square. Of mv square. And here the minus can be gets cancelled. And also write here the mass here this mass m1 is equal to capital M, that is the earth of the mass, and m2 is equal to the object of mass is m, and velocity is moving with velocity v is equal to ve. V is equal to v, and substitute in above equation we are getting here the g into capital M small m by r is equal to half mv square, and the mass can be gets cancelled. The mass and mass can be gets cancelled. And next we can write here the gm by r is equal to half v square. Here r is nothing but 2. The r is nothing but 2. What is taken by the distance between the center of the particle to the moving of a particle. Now for example, it is lifted off at height of h now. Then we are assumption by this total height, the small r is equal to capital R plus h. And now we can write the 2 is crossed by 2gm by r plus h is equal to v square. But here the compare with a radius, the height of the object is moving, it is a very less. That's why the radius is greater than of height h, and h value can negligible, and then we can write the ve is equal to the velocity, escape velocity of object is equal to 2gm by r. 2gm by r. We know that the relation between the small g and capital T, the g is equal to gm by r square. Take the cross multiplication, the g into r square is equal to gm. This value we can substitute here, that the escape velocity of a object is equal to under root of 2 into gm is equal to what we can, g into r square by r. Now it's negligible, that ve is equal to under root of 2g into r. See, this is the formula of a escape velocity of a object. The ve is equal to under root of 2 into g into r. G is nothing but to acceleration due to gravity. This is the constant value of earth surface, 9.8 meter per second square, and r is nothing but to radius of earth, 6,400 kilometer. Now we can substitute, and finally we get this is the value, that escape velocity of object 11.2 kilometer per second. Now the any object is moved with an a per second 11.2 kilometer, that time it is escaping of a gravitational influence and enter into the space. See, this is called as the escape velocity of a value. See, Nana, the next we discussing by the topic is the behavior of a body projected vertically up with different velocities from surface of a planet. See here, let us consider a body of mass m. Let us consider a body of mass m. The projected with velocity v from the surface of a planet. See, this is considered the planet. So this is considered the planet. Okay. Now this is the case one. This is how the consider the planet. Its mass is considered the capital M, and radius we are considered by the capital R. Radius how much is there? Capital R. Its center is considered by the O. Now the object, see, there is a body. The small body is placed on a surface of a earth. Its mass is M. Its mass is M. Now the projected with, this is the projected with velocity V. The projected with the velocity V. Then when the projected of the with velocity V, its velocity is less than of escape velocity. Okay, its velocity is greater than of escape velocity. See, that time this object is reached at the maximum height. And after under the gravity the fall to the surface of earth, because of here the this velocity is less than of escape velocity. See, the escape velocity means how much is there? 11.2 kilometer per second. This velocity is that less than of escape velocity. That's why this object is reached at the maximum height and return to the fall on the surface of the earth. Now then we can find out this how much of the height can be traveled by the object. See here, the total energy of surface is equal to total energy, the maximum height. Now here the total energy of the surface is nothing but the sum of potential energy and kinetic energy is equal to the total energy, the maximum height. Total energy at the maximum height. Now the potential energy means which is taken gravitational potential energy. The gravitational potential, the formula minus G capital M small m by R. Minus G capital M small m by R. See, this is the planet of the mass is capital M and the body of the mass small m. That's why the minus G capital M small m by R. Plus kinetic energy. What is the formula again? Half mv square is equal to total energy. What is the formula for the total energy? The G into capital M small m by the distance. Distance is nothing. The travel of the height. The total distance we have to take an R plus H. And we have the calculation. The finally we get, that is the height H is equal to R by n minus 1. This is the first case. The H is nothing but the height attained by the body, and R is nothing but radius of planet, and n is nothing but number of. N is nothing but what is the number of, that is the square is taken, n square minus 1. And now the second case, now taken by the case 2 here. In case 2, we are taken by the, again it's in a planet. See, this is how the planet. The planet of a mass capital M and center is O and radius is the capital R. Now the object is placed the surface of a planet. Now its mass is m. Now is projected is vertically upwards. Now it's moving with velocity v is equal to ve. This object of the velocity is equal to escape velocity. That time is enter into the space. Is enter into the space. That is enter into the infinity. That time its final velocity become equal to 0. That final velocity become equal to 0. See, now its object is moving. Object of the velocity is equal to escape velocity. Here this object of the velocity is less than of escape velocity. That's why it's reached the maximum and return back now. But here the condition, what is the object of the velocity is equal to escape velocity. Escape velocity. That means we taken by the formula h is equal to r by n square minus 1. N square minus 1. But here the both of them are equal, then we take the n is equal to 1. See, 1 whole square is nothing but h is equal to r by 1 square minus 1, that is equal to 0. It is taken by the infinity. The height attended by the object, the how much of the height is attended, this height is nothing but is enter into the infinity, nothing but to space now, is enter into the space. Now the discussing of the case 3. In case 3, we have said that again we are consider this as a planet, no? Planet. Its mass is capital M and its radius, how much is there? No? Capital R. And now the object is placed on a surface of a planet. Its mass is m. Now this object is projected the vertical upwards. Its velocity is greater than of escape velocity. So velocity is greater than of escape velocity. This moving with velocity is the greater than of a escape velocity. And ఇంకా ఎక్కువ faster move అవుతుంది. Then the total energy of surface of planet, the total energy surface of planet is equal to the total energy interstellar space. The total energy interstellar space, because of is enter into the space. Now that time where is it enter into the space, that velocity, the final velocity is not equal to 0. Here the final velocity equal to 0, here the not equal to 0, because of is moving greater than of escape velocity. Then the total energy of surface of the planet is equal to the sum of potential energy plus kinetic energy is equal to the total energy of the stellar. Again here the potential energy plus kinetic energy of it infinite. Then right here the potential energy. What is the gravitational potential? Minus g capital M small m by r plus half m v square. Half m v square is equal to minus g capital M small m by the distance. R is the distance. How much is there? Is the infinite plus kinetic energy half m v alpha square. How much is that? Half m v alpha square. See, now it take here the LCM. Here we taken the LCM, and the finally we get the minus 2 g capital M by r, minus 2 gm cap by r plus v square is equal to v alpha square. That is nothing but v alpha is nothing but the velocity at infinity. Velocity at infinity. Now this velocity of infinity is equal to under root of v square minus ve square. That is the nothing but to escape velocity. This is the formula of the when the object is moving the greater than of the escape velocity. The velocity at infinity is equal to under root of v square minus ve square. See, the next we discussing by the topic is the orbital velocity. Orbital velocity. See, let us consider this is an earth or planet now. The earth or planet. Now its mass is capital M, and its radius, this planet of the radius we consider the capital R, and center is O. Center is O. Now the one object, so the one object is height of h now, is height of h, is revolving around this planet, is revolving around this planet. So this is the nothing but just of we are considering by the satellite now. What is considered as a satellite is revolving around this planet. Now this total height, this total height is r is equal to capital R plus h now, capital R plus h. Now see here the this object, this is say the object or say the satellite now. Now the horizontal, the minimum horizontal velocity required, the minimum horizontal velocity required for an object, for an object revolving around the planet, revolving around the planet is called orbital velocity, is called as the orbital velocity. Now when this object is revolves around in a circular orbit, this force is extracted toward the center, is called as the centripetal force, centripetal force. So what is the formula for the centripetal force? The Fc is equal to mv square by r, mv square by r. But this object is moving with velocities v naught, and the small r is equal to how much is of height is there? R plus h, the total height. So right here, here v is equal to v naught and the small r is equal to capital R plus h. The substitute in above equation, then Fc is equal to mv naught square by r plus h whole square. This is considered the equation number 1. And also this equivalent opposite, this equivalent opposite, that another force is given by there, that is the gravitational force of attraction, gravitational force of attraction, force of attraction. See what is the gravitational force of attraction formula? The F is equal to G into m1 m2 by r square, m1 m2 by r square. See right here the m1 is equal to capital M and m2 is equal to small m. See right here, here m1 is equal to capital M, the planet of the mass, m2 is equal to object of mass, and small r is equal to r plus h, r plus h. And the substitute in above equation, this F is equal to G capital M small m by r plus h whole square. This is considered the equation number 2. Now here the both have the forces, the equal and opposite forces. That's why it is the equation from equation 1 and 2. From equation 1 and 2, the both of them have to equal. Then write here the mv naught square, mv naught square by r plus h is equal to G capital M small m by r plus h whole square, and the square and root gets cancelled, the small m gets cancelled, and this v naught is equal to under root of G m by r plus h. And here the radius of the earth is compared to the height, it is negligible now. The r is greater than of h, and this h value can be out to negligible. And also we know the relation between the small g and capital G, the gm is equal to r square, and the g into r square is equal to gm, and the substitute in the equation, the finally we get there's a v naught is equal to under root of g into r. See this is the formula of the orbital velocity of a object or satellite. Now this how much of the value is there, means the g is equal to what is the constant value? 9.8 meter per second square, and r is equal to radius of earth 6400 kilometer, and these two values substitute, and this v naught is equal to 7.92 kilometer per second. Now this object is required to revolve around the planet. See that velocity how much is there? 7.92 kilometer per second. So the next we discussing by the topic is relation between orbital velocity and escape velocity. What is the formula for the orbital velocity? The v naught is equal to under root of g into r. So what is the escape velocity for the formula? The V is equal to under root of 2gr. See, here we can observe the VE is equal to root 2 into root GR also we can write. But root GR is equal to how much is there? V naught. This escape velocity is equal to 2 root times of orbital velocity. This is called as the relation between the orbital velocity and escape velocity. And next we will be discussing by the time period of satellite. Time period of satellite. Time period of the satellite. See, we know the satellite is nothing but is revolving around any one of the planet. For example, we are considering this the satellite can be revolves around its earth. Now its time period, the t is equal to what is the time period? Distance by velocity. Distance by velocity. Distance by velocity. But distance is nothing but is moving on a circumference of a circle, that is equal to 2 pi r by its velocity. Which are the velocities there? Orbital velocity. Orbital velocity. Now we all know that orbital velocity formula, the t is equal to 2 pi into r by under root of g m by r. See, that of the formula for the orbital velocity. Orbital velocity. Now the squaring on both sides. Squaring on both sides. See what we are to getting now. See the squaring on both sides. T square, that is 2 whole square 4 pi square r square by the square and root can be gets cancelled g m by r. This denominator of the denominator take the numerator. See that the t square is equal to 4 pi square r cube by g m. See that means what is there? No? We have said that the Kepler say the third law. The square of the time period. The square of the time period is directly proportional to the cube of semi-major axis. Semi-major axis. So this is we have to the proof now. That is the square of the time period. And also we can write in terms of density. In terms of density. See that in terms of density we can write. See what is the in terms of density? No? The density is equal to mass by volume. No? Mass by volume. Then we can write the mass is equal to density into volume. See, it is just like of a spherical shell. What is the sphere of the volume? The volume of the sphere, that is equal to 4 by 3 pi r cube. What is the other? 4 by 3 pi r cube. But here the radius is considered with the capital R. That's why it's in the capital R cube now. This value substitute above equation. Then we can write here the t square. T square is equal to 4 pi square r cube by g into 4 by 3 rho pi r cube. G into 4 by 3 rho into pi r cube. See, now here this 4 can be gets cancelled. 4 and 4 can be gets cancelled, and pi 1 pi also will have to get cancelled, and this denominator of the denominator take the numerator, this t square is equal to 3 pi r cube by how much is there here? G into rho into r cube. G into rho into r cube. This is the formula of A. This is the formula of the time period in terms of density. The time period in terms of density. And next, the second one we have to discussing about this for surface satellite. For surface satellite. So what is the surface of the satellite? The surface of the satellite, that is the h is less than of r. And now the surface of the satellite, this height is can be negligible. What we are there only for the radius. See that time we can write the small r is equal to capital R. The times the small r is equal to capital R. Then substitute in above equation, the t square is equal to 3 pi capital Q by G into rho into capital Q, because of the small r is equal to capital R. Then this 2r can be cancelled. Then write the T is equal to under root of 3 pi by G into rho. G into rho. And also we have know that the time period for the formula. What is the time period? The T is equal to the time period of the formula. The T is equal to 2 pi into under root of R by G. The root of R by G. This G value and the rho value we can substitute. The finally we get the time period. The T is equal to 2 pi into under root of R by G. Now here there the one of the important point. In case of earth time period, in case of earth time period, so right here the in case of earth time period, earth time period, in case of a earth time period of surface satellite, of surface satellite, see that time period is T is equal to 84.6 minutes. Now this is the one of the important point. The surface of the satellite for the earth, the time period T is equal to 84.6. See, in the next we are discussing by the angular momentum of satellite. So what is the formula for the angular momentum? The L is equal to mv naught into r. The v naught is nothing but to the velocity of orbit. We can substitute here the m into, that is equal to under root of g m by r into r is equal to L. Now the squaring on both sides. The squaring on both sides. The L square is equal to m square g capital M r into r square, and this r will be gets cancelled. Then L is equal to under root of g capital M small m square into r. See, this is the formula of a angular momentum of satellite. For the surface of satellite, for the surface of satellite, the surface of satellite, then the h is the less than of r value. Then here the negligible of the h value, and also this small r is equal to what we can write r plus h, that is equal to g capital M small m square into r plus h at height. When the h is negligible, then we can write the L is equal to the angular moment under root of g capital M small m square into r. See, this is the formula of the surface of the satellite. Surface of the satellite. See, Nana, we're discussing by the geostationary satellite and polar satellite. The geostationary satellite is nothing but is called as the, if the time period of revolution, of an artificial satellite, is equal to the period of rotation of earth, such satellite is called as a geostationary satellite. Now these satellites are the how much of the height to can be rotated is nothing but to 35,800 kilometer. Now these satellites are revolves the west to east direction. This is the like west to east direction, and the speed of revolution is 3.1 kilometer per second. Its time period is equal to the earth of rotation, that is the 24 hours. Such satellite is called the geostationary satellite. And next we are discussing by the polar satellite. A satellite whose the orbit, the plane is perpendicular to the equatorial plane is called as the polar satellite. For example, this is considered the earth. Now earth is nothing but to, it have the east and it have the west and north south direction. Now this polar satellite can be revolves the north to east direction. This is the north of east direction can be revolves now. So that type of satellite is called the polar satellite, and it have the low altitude. The low is nothing but low height too can be revolves now. That height is how much is there? 500 to 800 kilometer between is moving off the polar satellite, and it is goes north to south and south to north. This is the, and the earth can be rotates. The earth can be rotates east to west, but here the earth can be rotated by the west to east. Now its time period is 100 meters. Its time period is the 100 meters. This satellite is called as a polar satellite. See, Nana, we're discussing by the topic is the weightlessnesses. The weightless is nothing but we know the weight. The which is called as a weight, Nana. The force with the which the force which with the earth attracts its body toward the center. The attracted body toward the center is called weight. Now the object feels weightlesses. The object is feels weightlesses whenever the normal reaction is equal to zero. Whenever the normal reaction is zero. That is possible when the net acceleration equal to zero. Net acceleration equal to zero. Now see the first case one. See, this is considered the lift. So this is considered the lift. Now the object is the freely falling in a lift. So this is the object can be placed and it is a freely falling in a lift. Now this acceleration A equal to G now. And its weight. Now the free diagram we can draw. This weight is acting vertically downwards and its equal and opposite is acting in a normal reaction. It is called the lift. And then find out is the resultant normal reaction when the lift is moving vertically downward direction with an acceleration A equal to G, that N is equal to M into G minus N. But here the G, A equal to how much is the G? We can substitute N is equal to M into G minus G, that is equal to 0. The net normal reaction is equal to 0, or so that the resultant force is equal to 0. Then therefore the weight operant weight is equal to 0. The operant weight is also equal to 0. And next one, the second case we are assumption by there. The second case, when the object, the consider the person in a satellite, the revolving around the earth, the closer to the surface of earth, that orbital velocity v naught is equal to under root of gm by r. The root of gm by r. See, now this is considered the orbit, and here the person, here the person can be there. Now its weight is acting downward direction and normal reaction is acting upwards, and it's move with velocity v naught. It's move with velocity v naught. Then it's the centripetal acceleration. The centripetal acceleration, the AC is equal to v naught square by r. V naught square by r. So the v naught is equal to what is there? Gm by r square. Gm by r square. And now you can draw here the free diagram of this one. Now this weight is acting downward direction and normal reaction is acting upward, and its acceleration, what is the centripetal acceleration, can be act toward the center, toward the center of a earth. And also again their operant weight, this operant weight is equal to 0. See, this is the two special cases of a weightless. Weightless. See, Nana, we're discussing some exercise problems on orbital velocity and escape velocity. See the question number 14. A satellite is revolving very close to the planet. The density is d and time period of revolution that planet. See, the time period of revolution of the planet is closer to this nothing but the surface of earth. That t is equal to 2 pi into under root of r by g. But r is the radius, g is nothing but to acceleration due to the gravity. We know that the relation between the small g and capital D, the g is equal to g m by r square. And the mass is nothing but you can do the density into volume. The volume of the sphere, how much is there? 4 by 3 pi r cube, that is equal to mass 1. And this m value we can substitute, the g is equal to g into capital G into 4 by 3 d into pi r cube by r square. R cube by r square. Now this r square and r cube can be gets cancelled. The g is equal to g into 4 by 3 d pi into r. This g value, the substitute in equation number 1. Equation 2 in equation number 1. So we get the time period t is equal to under root of 3 pi by d into g. D is nothing but to density, no? G is nothing but to the universal gravitational constant. Next, see the question number 51. A satellite is in a circular orbit around the planet. The time period of t, the radius of orbit is r, the orbital velocity v, and acceleration z. See, what is it? The satellite is in a circular orbit. See, this is the satellite in a circular orbit. The satellite in a circular orbit around a planet. This is the planet. This is considered the planet. This is considered the satellite. Satellite. Okay. Now then find its time period and acceleration. What is the time period? The time period t is equal to distance by velocity. Distance by velocity. The distance is nothing but the circumference of circle, that is the 2 pi r, 2 pi r. And the velocity is nothing but is the orbital velocity is taken by the v naught, 2 pi r by v naught. Then the velocity, we can write the velocity v naught is equal to 2 pi r by t. And then find its acceleration, that is the centripetal acceleration. Centripetal acceleration, because of this acceleration act towards is the center. This acceleration act towards the center, that is called the centripetal acceleration. The AC is equal to v square by r. V square by r. And next, see the question number 56. Question number 56. If the mass of the earth is m, its radius capital R, the gravitational constant g, then the speed required to given to the projected so that the does not return to the earth. Does not return to the earth is nothing but escape velocity. Escape velocity. The minimum velocity required for an object escaping from a gravitational influence is called as the escape velocity. That escape velocity v is equal to under root of 2gm by r. 2gm by r. This we can write the direct formula. And next, see the question number 59. Question number 59. C is given the ratio of time periods of satellite at the height of h1 and h2 for the surface of earth. For the surface of earth. See, this is the earth. No? This is how consider the earth. And the two satellites. This is how the first satellite. No? The how much of the height is given by the h1 height. And the second satellite is revolving at a height of h2. No? How much of the height is given? h2. Then find the ratio of its time period. We know that the square of the time period is directly proportional to the cube of semi-major axis. Cube is nothing but radius. Now this total distance. See, now it's a radius of earth. How much is there in a capital R? And capital R to the height. And that is the T is directly proportional to the R to the 4 of 3 by 2. No, it's denominator question. Now, but the small r is equal to R plus H1. No? And another one is taken the R1. R2 is equal to taken the R plus H2. That time its time period is T1. And here the time period is considered T2. So then take the ratio. And T1 by T2. The T1 by T2 is equal to R1 3 by 2. R to the 4 of 3 by 2. Then T1 by T2 is equal to R1 is equal to capital R plus H1 by capital R plus H2 whole to the 4 of 3 by 2. No? Whole to the 4 of 3. Because of here the square of the time period is directly proportional cube of semi-major or the distance between the center of the earth to the revolve of the height of satellite. No? See, this square is negligible, 3 by 2. The total distance r is equal to nothing but the total distance r plus h1 and another to the r plus h2.